What's good, y'all, and welcome back to another edition of Mr. Fitzgerald's biology class. Today, our focus is on particle movement as well as solution types. So we're going to talk about what's around the cell, the liquids that are around the cell and inside the cell, and have specific names for them. Also, how those particles are going to move both inside and outside the cell, so you know how the cell gets its stuff. Now, before we do that, let's kind of activate what we already know. Going back to physical science or back to IPS, whatever your experience has been. Let's say we have a situation. I have a student in class by the name of Sally. She's got a brand new perfume. She loves the smell on it. She tries to stand in the corner of the room to try to spray her perfume as not to bother me and my allergies. Will her idea be successful? Will I be saved with my allergies from her perfume? Well, unfortunately not. And the reason we know that probably it's not going to work is because we know that smells spread in a room. If she sprays that perfume, it's going to spread out. So eventually, on the other side of the room, I'm going to come in contact with it, and depending on how much of it makes its way over there and how much she sprays, I might start coughing, sneezing, or something else. So that process is known as diffusion. So what you already know is kind of about gases and how they'll move and expand and take up space. But the true definition of diffusion is when you take the movement of particles from an area of a lot of particles, known as high concentration, and you move them to an area of low concentration, or not a lot of particles. So for example, we have maybe extra particles over here, right? If I have a lot of particles over here, they're gonna flow to where there's not a lot of particles. If Sally sprays her perfume in the corner of the room, there's a lot of particles there of perfume. They're going to slowly spread their way across so that way they can spread themselves out and get evenly distributed. So the idea of this is going from where you have a lot of something, again, high concentration, to where you have a little of something or a low concentration of it. And that's just spreading those particles out, okay? Now, if we have some equal stuff, okay, as we move across and these things spread out, it does get a very specific name for that, and that's called a dynamic equilibrium, okay? So equilibrium means equal. If you notice, the flow here is equal. So there's, equal in both directions, kind of looks like an equal sign, equilibrium. But it's called dynamic because it's moving, okay? Once particles get on this side, they don't just stay there. One of them will move across and then another one will flow back. Right, so they're exchanging constantly. Just like how the air in the room is not static around me, it's constantly moving. Sally sprays her perfume in the corner, it makes its way across the classroom, and I can interact with it. And I can, breathe it in and breathe it out and spread those particles even more. So things spread pretty quickly in an indoor closed-in space because those particles are going to keep moving at a dynamic equilibrium. There is no overall change, that's why it's called an equilibrium, but there is still movement of particles. Again, these things are not locked in their positions. Once they get on this side over here, they're not going to stay here forever. They will eventually move back and forth across, but just equally, as one or two go over, one or two come back to keep it balanced, okay? Now, osmosis comes into play, and again, same diagram there. You can see that dynamic equilibrium as they were moving to get equal on both sides. But osmosis is a very specific diffusion of when we're only talking about the movement of water. So instead of talking about the movement of a gas or the movement of other particles, we could be talking about water specifically through osmosis. So again, water wants to go from where there's a lot of water to where there's a little water. Think about it if I have a bucket full of water, and I spill it out on the table. The water wants to spread out. It wants to occupy that new space that it can because the surface of the floor is flat, whereas the bucket, it was cylindrical in shape. So it'll occupy that space or spread out to where there's that low concentration trying to get equally all throughout, where it was a high concentration or tightly packed in the bucket. Okay? And the same thing will happen with cells and with the area around cells. Water will want to move across, just like these particles do, where one comes over, one goes back. But it'll want to move across to where it's balanced on both sides. So it wants to be equal. All right, and this does occur for water specifically with the cell membrane because the cell membrane is called semi-permeable or selectively permeable. If you did your cell membrane reading, you should know selectively permeable or semi-permeable membranes allow certain materials in and keep certain materials out. Water is one of the few materials it allows to just go in and out whenever it wants to, so that way it can try to balance itself on either side. So it does help the cell maintain what's called homeostasis, or balance, because it's going to equally move across that selectively permeable membrane. Some other particles might not be able to move across, so therefore they're not able to permeate or get across the membrane. Okay. So this structure here would be the cell membrane in this diagram. You can kind of see, if you look at it closely, it's got like these two areas here with, it looks like little ladders. So you can imagine those as the phospholipid bilayer with the polar heads on the outside, or the hydrophilic heads on the outside, and the non-polar hydrophobic tails that run down the middle. Again, refer to your cell membrane reading if you're a little confused at what I just said, because it does talk in detail about it. Now, there are specific types of solutions. As we're going through them, I want you to visualize in your head where water would move, okay? So in these situations here, I'm gonna have the inside of the cell. It's always gonna be represented down here. The outside of the cell is gonna be this nice blue color. You can imagine that's water, right? There is some water inside the cell, but they're trying to define the boundary. So they made this one orange, this one blue. And these little particles, pretend they're salt. Something that's easy that you're aware of. So they're not water, they're just something that's in water, something that's dissolved in water. So we'll say it's a salt, okay? So in an isotonic solution, we are equal. If you count the dots, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. I have 6 dots on each side, so I'm equal. That's why it's called isotonic, okay? Tonic, I'm referring to mostly the particles, or what's dissolved in the water. So in this case, our little green dots were our salt, and we're equal on both sides, so we have an isotonic solution. So I have the same amount of solutes or particles both inside the cell and outside the cell at the same time. Now, as you're writing that kind of down, hopefully you're thinking in your head, okay, where would water move? Water wants to go where there's a lot of water to where there's a little water. I'm assuming outside the cell has a lot of water because it's blue, but maybe inside the cell has water. Well, think about that word isotonic. Iso again means equal. So water wants to be equal or flow equally. In this situation, it wants to keep a balance, okay? It wants to keep the same amount of water per particles. So it will freely flow across both sides. So you'll get water moving in and out pretty frequently in this kind of a solution. Okay, so isotonic, they move equally. If you need to pause to draw this picture, please do so. It is a very beneficial photo as we're going through these. All right, the next one we're going to talk about is hypotonic. Hypo is a little bit different. If you look at your particles, you have 6 particles still inside the cell, but only 1 on the outside. Okay, so outside has a lot less. Hypo means less or under. Less or under. So in this situation, outside the cell, I have less solutes, or less salt, or sugar, or whatever the particle I'm dissolving in water. I have less of it outside the cell than inside. So the question then is, which way will water flow? Well, who do you think has the most water? Outside the cell that has a little bit of salt, or inside the cell that has a lot of salt? Hopefully looking at this, you go, well, if I have a little bit of salt, I probably have more water than if I have a lot of salt. And that's true. So water in this case will flow inside the cell. It's going to want to go to where the salt is, because there's probably extra water here. That's why it's so small in concentration or low in concentration. It wants to help spread these ones out. So you can imagine water's going to flow into the cell, making it kind of swell up and get a little bit bigger in this kind of hypotonic solution. On the other hand, there could be a hypertonic. Okay, if you look again at the particles, still 6 on the inside, but we got like 14 or so on the outside. I forgot what the count is. If you want to count it and message me, by all means, have at it. But hyper means above or extra. There's a lot more out here than there is in here, okay? So this one, you have a much greater amount of solute, or things that are dissolved outside the cell, than you do inside the cell. So in this case, which way is water going to flow? Well, before we looked at, water likes to go to where there's the most particles, where there's the most things that are dissolved in it, so that way it can help spread them out. So in this situation, instead of water flowing into the cell, water is going to flow out pretty rapidly, because there's going to want to spread out these particles and kind of make that solution match more of what's inside the cell, all right? So what happens to the cell, unfortunately, instead of swelling up, it's losing a lot of water, so it shrinks down, okay? So you can get some changes in your cells. When you're dehydrated, you haven't had a lot of water, you build up a lot of salt in your bloodstream and outside your cells. So you're actually losing more water from your cells, and that's why you really need to replenish when you're doing a lot of heavy exercise. All right, so again, the different types of solutions, kind of looking at them from left to right. The hypo, meaning I have less dissolved particles around the cell than inside the cell. Iso means I have equal particles on both sides of the cell, inside and out. And then hyper, I have a lot more particles outside the cell than I do inside the cell. In each case, on the left one, the hypotonic, remember water's gonna flow into the cell, causing it to swell up because there's more water outside than there is inside. Isotonic, water's gonna move equally because iso means equal, so it's gonna flow equally across the membrane. And then finally, with hypertonic, water's gonna wanna flow out of the cell, trying to spread out these particles and unfortunately shrink in size.
A little light practice here. I want you to look at the two photos and kind of think about those particles that are there, those little dots that would represent maybe sugar or salt or something that could dissolve in water. I want you to guess what you think the way the water moves. So in that first picture, it looks like I have more dots on the outside of the cell or the circle than inside. So water in this case is going to want to flow out of the cell. Remember, this would move the water out so it could spread those particles out in a little bit more distance and kind of give them more space. And this would help create that equilibrium where you have an equal amount of dissolved salt inside and dissolved salt outside the cell. Even though the actual numbers of particles will be different, the percentages is what the cell is trying to achieve equality with. So it's trying to get an equal percent of salt per water outside of the cell and then salt per water inside of the cell. On number 2 there, I have a lot more salt inside the cell or particles inside the cell. So in this case, water is going to flow into the cell. So that way it can actually spread out those particles inside the cell. And again, it wants to try to get that equal percentage or the same amount of salt per water inside of the cell as outside. So that's that goal of dynamic equilibrium. All right, so the last piece that you're going to work on is to create a foldable. So on the front side of a sheet of paper, you fold it in half basically, and you write down the 5 vocab words we've done today: diffusion, osmosis, isotonic, hypertonic, and hypotonic. If you put them out of order, it's okay, as long as the information that's inside the folded sheet of paper matches what's on the outside, you'll be fine. So inside the sheet of paper, on the left-hand side of the inside of the sheet of paper, I want you to actually write the definitions for the words. So when you unfold that sheet of paper, you got diffusion at the top. On that inside pamphlet, basically right underneath the word diffusion, you're going to write the definition for diffusion using 5 words or less. Okay, so give me a short phrase that tells me what diffusion is, what osmosis is, what isotonic is. Very short. You maybe could use 1 word for some of them. So that way I get an understanding that you can kind of break this down in your own words. And then on the right-hand side of that paper, you're going to show me a picture that would represent it. So whatever creative outlet you want to use on that one, you can use some of the photos that I've used in my notes to help you out a little bit. But however you choose to represent those words diffusion, osmosis, isotonic, hypotonic, and hypertonic, make sure you go ahead and do that for a picture on the inside as well. So on the front of the foldable, again, you got the vocab words, the front of the sheet of paper. On the inside of the sheet of paper, on the left side of the crease, you're going to have the definition using 5 words or less. And on the right side, you're going to draw a picture to coincide with it. Make sure you take a photo of basically your whole foldable and get it uploaded to Canvas for your grade. That's all I got for today. Have a great day.